So first we're going to deal with Lewis structures or Lewis dot structures, and then we're going to deal with the Vesper theory, which sounds crazy, but it's really much easier than it is, okay? So let's go ahead, go down here to Lewis dot structures. So Lewis dot structures or dot structures, they're a way to depict or to picture so that people can see those valence electrons and how they interact in bonding. So valence electrons are, as you probably know, those are the electrons that are in the outermost shell of an atom. So let's just take hydrogen. This is going to be the nucleus of hydrogen, and it has one energy level. And we know that based on the periodic table. We'll talk about that in just a little while. Hydrogen has one energy level, and its valence electron is actually right here. Well, it could be anywhere, but it's on the outermost shell, okay? The same with helium. Helium has that one energy level. Let's go back. So helium right here, helium has that one energy level right here, boom. But it has two valence electrons. So it has two valence electrons. So that's the outermost shell because it's in that first energy level. Now if you jump down to, say, potassium, which is in the fourth energy level, so potassium is going to have 4 of the energy circles around it. So we'll put a K here, and I'm going to erase this in a minute. We'll put a K here, and we'll put 4 energy levels around it. 3, 1, 2, 3, 4, okay? And as you know, these electrons are going to fill up the outer shell, or fill up to the outer shell by filling in the center shells. So we're basically going to fill this in. The first shell holds 2. And every other shell after that holds 8. So we'll just put them in there like this, okay, just to get rid of it. So, but if you come down to the final valence shell, which is the outermost shell, potassium is going to have 1 valence electron in it because it's in group 1. So that is what it means by valence electrons. Valence electrons are those electrons in the outermost shell, okay? So those are valence electrons. I'm going to erase that. You can always go back, rewatch it, okay? So Lewis dot structures are taking those outermost and only the valence electrons and really showing how they interact in bonding, specifically if there's 2 or more atoms. So let's talk about this, and it looks like you have, because it's up there, the Octet Rule. So the Octet Rule is this. The Octet Rule states that every atom besides hydrogen and helium, they want 8 electrons in their outer shell. 8 electrons means they're full because all those shells can hold up to 8, and if they have a full shell, they're stable, they feel good. If they feel unstable with 7 or less, then they're gonna get stressed out and want more, okay? They just want to have more, all the way up to 8 valence electrons, okay? So it stabilizes them. So the Octet Rule says that every one of them, besides hydrogen and helium, every atom on the periodic table besides hydrogen and helium want 8 valence electrons. Okay, so that's the Octet Rule. That plays into the Lewis dot structures because what we're going to try to do is we're going to try to make sure that every atom involved in a Lewis dot structure has 8 valence electrons in it. It's going to be a little bit weird, a little bit funky, but we'll see how that goes. Okay, let me show you, just probably as a refresher, but I don't know who your teacher is, but let me show you how this goes. So you can discover the number of valence electrons by looking at the groups on the periodic table. So groups are those vertical columns, those up and down columns, vertical columns. And those vertical columns have the whole column has the same number of valence electrons in it, which means that they have similar characteristics. They react similarly, that's hard to say, but they react similarly. So the group 1, vertical has 1 valence electron. Group 2 has 2. 3, we skip the transition metals because you can't really ever tell where the valence electrons are in the transition metals because they are in like a sea of electrons or moving around. That's what makes them shiny and conductive. So you have 3 and then 4 here, 5, 6, 7, and then finally in the noble gases you have 8, and that makes them inert. And they don't react with anything because they're fully stable. Remember, they want to be stable. And 8 valence electrons in their outer shell makes them stable. So this is how we're going to discover how many valence electrons to put into this Lewis dot structure by just simply looking at where the element is in the group. So say, for example, just really quick, say we're looking for boron. Boron is the first element on the 3rd group, and that element is going to have 3 valence electrons in it. If you go down that group, even to titanium, which is down here, titanium, same group, is still going to have 3 valence electrons. And if you move over to, say, sulfur, sulfur is right here in group 6. And so sulfur is right under oxygen. Sulfur is right here, and that's going to have 6 valence electrons, just like oxygen would. Okay, so summary so far. We're doing Lewis dot structures. We're talking about valence electrons, which are those electrons in the outermost shell, and how Lewis dot structures are showing how those valence electrons interact in bonding. And you find out your number of valence electrons by looking at the group, the vertical columns, and you're trying to fill out this octet rule, meaning all atoms besides hydrogen and helium want 8 electrons in their outer shell, their valence shell. So let's talk about the steps of drawing Lewis dot structures. I see them up there in the sheet, and they might be these exact ones. I didn't look through the sheet too much, but I see the problems we had to do. So here are my steps. Number 1, to do Lewis dot structures, I count the number of valence electrons. And I do that just by looking at the group number. If there's 1, if there's 2, then I count those both and I add them together. So I count and add, count and add. And that goes for electrons in each of the atoms. Say I have H2, which I do down here. H2, I take the fact that hydrogen has 1 valence electron, but there are 2 hydrogen. So I'm going to do 1 times 2, or 1 plus 1, either one. And I'm going to get the fact that I'm going to have 2 electrons between the 2. Okay, so I'm just basically counting up every atom that's involved in the actual Lewis question, and then I'm writing it down. If I have more than 1 atom, then I draw that skeletal structure. And we're going to do this again down here, but let's just say the skeletal structure for hydrogen is going to be this. And these lines, this represents a single bond, single. This represents a double bond, like this is easy. This represents a triple bond, and you're never, usually, generally not going to have a quadruple bond. So you'll see that. This is the skeletal structure for hydrogen, H2. So then I place the remaining, if I have them, electrons around the outside atoms, okay? So there's no real outside atoms in this equation right here. There's just 2 atoms. But if I had 3, like we'll see, then I place the remaining electrons around the outside atoms. Then I place any leftover atoms or electrons around that central atom that's going to be in the middle. And then I just do a check and final count all of my electrons. So we just did H2, so let's do that again. I'm going to do it in white, so let's do H2. So I look at my periodic table. My periodic table tells me that hydrogen is going to be right here, okay? Hydrogen right here, group 1. So I know that I have 1 valence electron for hydrogen. I've got 2 of them, so that means I've got 2 valence electrons. And then I'm supposed to fill out that octet rule. Now, hydrogen is going to look like this, bonded together, 2H2, right? So I got 2 H's, 2 hydrogens. Now, the octet rule states that they want 8 valence electrons, except for hydrogen and helium. So if we look down here, this is the Lewis dot structure for H2, because these are fine with 2, and these represent 2 valence electrons. This line represents 2 valence. These lines represent 4 valence. These lines represent 6 valence. Okay, so it just kind of gives every line you have represents 2. So 2 and then 2. Okay, so let's do O2 Lewis dot structure. So I look up here and I see oxygen is right here, and that's in group 6. So it's going to have 6 valence electrons, and I've got 2 oxygen. So 6 valence electrons times 2 is going to give me 12 valence electrons. So I write them down. So now I draw the skeletal structure. So I go 0, O and O. And now I'm going to try to fulfill that octet rule. Remember, every atom wants 8 valence electrons. I've got 12 to play with. How are we going to do this? 16 would be easier, right? But we got 12, so let's just see how we're going to do this. So we draw our skeletal structure. First, we put our, I'll change the color up here. We draw our skeletal structure, which we put a single bond first in here. Okay, single bond. Now, once I bound them together, then I place the remaining electrons, remember up here, around the outside. So basically, I've got 2 valence electrons here. I'm going to put one here, one here, one here. Now I've used up 5, right? Minus 5. And then I'm going to put one here, and one here. So now I've used up 6. So 1, 2, 3, 4, 5, 6, 7, 8. I've used up 8. That leaves me with 4 more valence electrons left. So now I'm going to put one here, and then one here, and then one here. That's 3, and then one here. So I've got all of my valence electrons in use. But if you look at it, this atom is fine right here. Right here, it's fine because it's got 2 right here, 2, 4, 6, 8, the octet rule. Okay, that's full. And then I look over here though, I got 2, 4, 5, 6. So I'm missing, or 2, 3, 4. I'm missing 2 valence or 4 valence electrons on this side. So now I've got to figure out how to get both of these atoms with 8 valence electrons. So now I'm going to just do some like puzzle shifting, okay? So let me clean this up just a little bit and we'll start again. So I got my oxygen right here, oxygen. And I've got my bond, and I've got my valence electrons right here. Now I'm just putting them in the way I had them, okay? Now I'm trying to figure out how to get, how do I get 8 valence electrons over here as well and not really eliminate this one, because I don't want this one to be unhappy. So what I can try to do is just try to start like figuring stuff out. Okay, so I need at least 2 more valence electrons over here to make this happy, okay? So what I'm going to do is I'm going to steal 2 of these guys, okay? I'm going to steal 2 of these guys, and I'm going to just put them over here, okay? So now I got 2, 4, 6, and now I got 2, 4, 6, 8. That's still off, so I know that didn't work. So what I need to do is I need to come up here, and what I'm going to do is I'm going to steal these 2, and I'm going to turn this into a double bond, okay? So now I got a double bond. Okay, and that double bond is going to give me 2, 4, and these 2 apply to both atoms. 2, 4, 6, 8. This one's happy, right? Happy. Now I got 2, 4, 2, 4, 6, 8, and this one's happy. This one over here is happy too. Perfect. So that is the Lewis dot structure for oxygen. Let's draw it one more time just so it's clear. Oxygen, oxygen, double bonded, and then 1, 2, 3, 4, 5, 6, 7, 8. And that is a fully completed. And the reason why I moved those valence electrons is what we'll see in the Vesper theory in just a moment. So let's see. So that is going to be my Lewis dot structure. Everything is fully completed with 8 valence electrons. Both of them are happy. They're all cool. Okay, so let's do BH3. Okay. In fact, let me just take this, move this out of the way, and give myself some more space for BH3. Okay. So BH3 is going to be right here. How do I discover my valence electrons? I just go up to the top, up to my periodic table up here. B is going to be right here. B, boron, and I see that has 3 valence electrons. So I'm going to come down here and I'm going to put a 3 right here. I'm going to come up here, and where's hydrogen? Hydrogen, again, is right here, so I know it's got one valence electron. I'm going to put a 1 right here, 1 right here. Okay, so I've got 3 thus far plus. I only have 1 boron, but I've got 3 hydrogen. So that's going to give me 3 plus 1 plus 1 plus 1. And that's going to give me what? 6 valence electrons? 6 valence electrons. This is going to be pretty tough to figure out BH3, because now that we have BH3, let me make sure that's BH3. Yep, BH3. Now that we have that, we only have 6 valence electrons, 3 atoms. How are we going to get 8 electrons around these atoms? Well, let's try it. So, number 1, we've counted our valence electrons. We know we got 6 valence electrons. Now we're going to do our structure. So our structure is going to look like this. We're going to put a B here, B here. We're going to put H's around it. We're drawing our skeletal structures. We're going to put single bonds. Remember, these are 2. They equal 2. Up here equaled, with oxygen up here, this was 2, this was 2, so the double bond is going to equal 4 valence electrons. But these are 2. Now we're going to put our H's around, okay? Here's our H's, H, H, okay? So we've got these full. So we've got 2, 4, 6 valence electrons already used up. 2, 4, 6 valence electrons already used up. And so this is an exception to the rule, because all we have is boron and hydrogen. And boron is fine with having 6 valence electrons in its outer shell. It's just fine as long as it's bonded to other atoms like hydrogen. That's fine. So I know that gets confusing. There's all kinds of exceptions to chemistry rules, and you wouldn't have known that unless somebody had told you. But that's just how life goes. So just know that boron at this point is fine with having 6 valence electrons. It's not fully happy, but it's cool. You know what I'm saying? It's not like super satisfied with life, but it's like, okay, I can deal. So that's the structure for boron, as well as the Lewis dot structure for it. Let's do this last one, and then I gotta go to lunch duty, or your mom's gonna be mad at me. So OH minus. Now you know probably that this minus means that it's got 1 less electron than it would have, or 1 more electron than it would have if it was neutral. The negative means that the electrons are more than normal or more than neutral. So we look up here at our periodic table, and we see that oxygen again is in group 6, so it's got 6 valence electrons. So I'm gonna come down here and I'm gonna put a 6. I'm going to come over here to hydrogen, and I know hydrogen has 1 because it's up here in group 1, right? Hydrogen's in group 1 right here. Then I'm going to come down here, so 1, and I've got 1 hydrogen, but I've got this extra electron, okay? This extra negative right here, which is going to give me plus 1. So now I know I got 8 valence electrons. 6 plus 1 equals 8 valence electrons. So now I'm just going to put my my Lewis structure together. And hydrogen never wants to be the central atom. It always wants to be the outside atom. So we're going to put oxygen right in the middle. Oxygen right here. And we don't have 2 hydrogens. We only have 1. So we're just going to put a bond to a hydrogen right here. And then we are going to fulfill and fill out the remaining valence electrons. We're not going to put them around hydrogen, because hydrogen, remember, is fine with 2, and this represents 2. So hydrogen is happy. It's cool. It's totally stable with life. Okay. Oxygen, however, at this point is not, so we need to put our valence electrons in, and we have used 2. 2 minus 2, so we got 6. Well, good for us, because oxygen wants 6 more. So we're going to put our 6 valence electrons in. 1, 2, 3, 4, 5, 6. And so now we have our structure, as well as our Lewis dot structure for OH minus. OH minus is going to have 6 valence electrons around the oxygen and 1 bond to the hydrogen. 1 bond to the hydrogen. So when we come back in the next video, I'm sorry this is so long, but I can't do anything else about it. When we come back to the next video, we'll do a couple more Lewis dot structures before we get into Vesper Theory. But let me give you a preview on Vesper Theory. Vesper Theory is going to take these Lewis dot structures, and these are like 2D, like you're looking at a piece of paper, right? You're looking at a piece of paper. Well, Vesper is going to take this 2D image and turn it into a 3D. It's going to turn it into a 3D image for us, okay? So that we can see what this molecule actually looks like. So that's what Vesper Theory does. It's called valence shell electron pair repulsion. That's what Vesper Theory is, valence shell electron pair repulsion. So that's what we're going to do. And hopefully that helped for a minute, and I'll see you next video.